In today's lecture, we will look at conservation of energy. So, in the previous video, we defined the concept of potential energy. But what's its use? Well, it turns out that if we add kinetic energy and potential energy, we can look at a quantity called mechanical energy. Is this useful? In the absence of dissipative and non-conservative forces, like friction or drag, and also in the absence of external forces, then the mechanical energy, EMEC, is conserved. So, for an isolated system where isolated tells us that there is no external force doing work on the system, and where we have no non-conservative forces doing work, so no friction or drag force doing work, in such a scenario, the mechanical energy is conserved, which means the initial mechanical energy is equal to the final mechanical energy. Let's use this to solve some problems. So here's the problem. We have a pendulum. The length is L, which is 20 centimeters. The mass of the bob is 500 grams. And it starts from rest here at 60 degrees. And it's released from rest and it swings over and reaches 30 degrees over here. Obviously, it'll continue past that, but what we're asking is how fast is it moving when it is at this position. Alright, let's try and solve this problem. So we are going to use energy conservation, which tells us that E initial equals E final. We consider the two kinds of energy, kinetic energy and potential energy, and so we have K initial plus U initial equals K final plus U final. Now we know that the initial kinetic energy is 0 because it starts from rest, and we know that the type of potential energy is gravitational potential energy. The form of the gravitational potential energy is mgy. So we need to know the y-coordinate here and the y-coordinate here. Let us pick this position, the lowest position of the object, as y equals 0. That way all our positions will have positive y-coordinates. So now we mark y equals 0 at the lowest position. We have y initial is the initial height at the starting position, and y final is the final height. And we know that this height is L. Well, using the angles that have been given, we can see that y initial is equal to L minus L cosine 60, because this is L and this is L cosine 60. So L minus L cosine 60 degrees would be y initial. Similarly, y final would be L minus L cosine 30, which would give us this y final. So, plugging all this information into our energy conservation equation, we get 0 plus mgl times 1 minus cosine 60 degrees equals 1/2 mv squared plus mgl 1 minus cosine 30 degrees. And now we have the values for mgl and the angles, and so we can solve for the speed v. Now, you might have worried about one detail in the previous solution. I chose the lowest point of the oscillation to be 0 height. And so any object at that height had 0 gravitational potential energy. But why did I choose that point? Why not some other point? Why not, for example, the high point where the string was attached? Could I choose some other point? Could I choose my initial height as y equals 0 or my final height as y equals 0? And would it affect my results? So it turns out there is no special height where I need to set my origin. I can choose any height that I want to be the y equals 0 height, as long as I'm consistent throughout the problem. So I can choose any point to be my origin, and then all the objects at that height will have 0 gravitational potential energy according to that coordinate system. So how does that work out mathematically? What's the justification there? Well, remember when we used the connection between work and potential energy to find out an expression for gravitational potential energy? We set the work done by gravity to negative delta U of gravity. And then we expanded that delta U into U final minus U initial. There's the minus sign outside. And we previously found the work done by gravity, and that was minus mg y final minus y initial. And then we set both sides equal to each other, and we compared, and we saw that, oh, okay, it made sense if u final was the same as mg y final, and u initial was the same as mg y initial. This was covered in the previous videos, so make sure to take a look at that. Well, let's go through the same steps, but now, once I reach this step, going to the next step, let me make one slight change. I am going to stick in, instead of just having y final, I'll have y final minus y naught, and instead of y initial, I have y initial minus y naught. Now obviously I can't just randomly stick in terms, but if you look carefully, you see that the extra term that I have here, right, the extra term here is plus mg y naught, plus because you have two minuses here, right? And the extra term that I add here is minus mg y naught, and minus because you have 1, 2, 3 minuses. And so I have just added and subtracted mg y naught on the left hand side. So I haven't really changed the left hand side at all, because this is basically just 0. So I haven't really changed the left hand side. But now when I compare the left hand side and the right hand side, I can see that, oh, u final goes with this term, u initial goes with this term, and so we have that the potential energy due to gravity is mg parentheses y minus y naught. And this y naught was pretty much completely arbitrary. It was just some constant y naught that I picked. So y naught is just some constant height. I can pick it however I like, and as long as I keep it constant throughout the problem, it won't really affect anything, right? All that will happen is that when y is equal to y naught, the potential energy will be 0. And why does this not make any physical difference? Because we're never interested in how much the value of u is at any one point. We're only interested in how u changes between 2 points. That is, we're interested in the difference of u final minus u initial. And so when I do that subtraction, the y naught term disappears, just like we saw before. And so adding or subtracting the same constant from both u final and u initial will not change anything. So if y equals y naught, then u gravity equals 0. So whatever height we choose for y naught, that is the height at which u gravity is 0. And all we need to do is just choose one height to be y equals 0 for a single problem and just keep it consistent throughout that problem. Alright, but what about spring potential energy? With spring potential energy, we take the spring to have 0 potential energy when it is at its natural relaxed length. That is, when you aren't stretching the spring or compressing it, when it's just at its natural length, that is when it has 0 potential energy. So now let's solve a problem that uses both spring potential energy and gravitational potential energy. Alright, read through the problem, try it yourself first, and then we'll go over the solution. So now we continue with the solution. I'm going to look at different situations that occur during this problem. So our first initial situation is here when the mass is just released. Okay, so it's a height h above the spring platform. The spring is completely relaxed, and the height, as I said, is h, and the mass is just been released, so it has no speed at this moment. Now the next situation that I'll look at is when the mass has just hit the spring. So, well, or if you like, it's just before the moment of collision. So the mass is moving with its maximum speed at this point, but the spring hasn't yet started compressing. Okay, and the height of the mass we can take to be 0 if we take this as our 0 height. And now the third situation is the mass has compressed the spring, right? So you can see that it's at a lower height now, and the mass has come to a stop. So the spring is at maximum compression, the mass has come to a stop, and if we were to let it continue, then the spring would launch the mass back up. But we're going to ignore that for the moment and just focus on how far the spring has been compressed, because that's what the problem asks us for. So let's define a few different things. So as I mentioned before, we will take this natural position of the spring to be the y equals 0 height, so that the mass starts at a height h above, and we will take this final position to be the y equals negative s. So it has gone a distance s below y equals 0, so we have y equals negative s. Alright, so we're going to use energy conservation, so let us set that up. So since we have two types of potential energy in this problem, we have K initial plus U gravitational initial plus U spring initial equals K final plus U gravitational final plus U spring final. And our initial situation is this, and our final situation is this. So let's plug in what we know. So the mass starts at rest, so K initial is 0. The initial height is h, so we have gravitational potential energy of mgh, and the spring is initially at its relaxed length, so it's neither compressed nor stretched, so the spring potential energy is 0. In the final situation, the mass has again come to a stop momentarily, so K final is 0. The y position is negative s, so our UG final is mg times negative s, and the spring is now compressed, so our U spring final is 1/2 ks squared. And that's it. We are given m and h and g as constants that we know, and so we have a quadratic equation for s. So we've brought all the terms to one side, and we have now this quadratic equation for s. You can see there's the s squared term here, the s term here, and the h term here, and we can now solve this quadratic equation for s. And we'll take the positive value because we've already accounted for the minus sign over here. Okay, and that's how we solve this problem. So until now, we've been looking at situations where the isolated system had, well, by definition, since it's isolated, no external forces acting on it, and also no dissipative forces acting on it. But supposing our system does have dissipative forces like friction, how do we account for their influence? Because after all, in the real world, most cases we do have friction. So we know that the work done by friction turns kinetic energy into heat energy. So the work done by kinetic friction, where there's sliding going on between two surfaces, is usually negative, I won't say always, but it's usually negative since the kinetic friction opposes motion. So in other words, the object is moving in one direction and the kinetic friction is in the opposite direction because it's trying to oppose that motion. And so we see that the work done is negative since the angle between them is 180 degrees. So since heat is being released, we will have the work done by friction is equal to negative delta E heat. In other words, the work done by friction is usually negative, and so in order to ensure that delta E is positive, we have this additional minus sign over here. So let's put together everything that we know about potential energy and friction and the work energy theorem. So the work energy theorem tells us that the total work done on a system is equal to delta K, that is the change in kinetic energy of the system. Now we are going to divide that work total into a bunch of different forces. So we have possibly the work done by gravity, the work done by the spring force, if there's any, the work done by friction, and then we have work done by other forces. And all of that adds up to work total and is equal to K final minus K initial. So we know that since gravity is a conservative force, we can replace it with negative delta U. Since the spring force is also a conservative force, we can replace the work done by the spring force by negative delta US. The work done by friction, we just said, could be replaced by negative delta E heat, and we leave the work done by other forces alone. And so now moving all these to the other side, we have work done by other forces is equal to change in kinetic energy plus change in gravitational potential energy plus change in spring energy plus the heat released. And we can expand out all those deltas, right? So we have final minus initial. And we can group together the initial terms and group together the final terms. But then looking at this is K plus U, and that's just mechanical energy. So we have the work done by other forces is equal to the final mechanical energy minus the initial mechanical energy plus the energy released as heat, or the work done by other forces is equal to delta Emech plus delta E heat. Or let's look through that again, but calling them slightly differently. We see that from the work energy theorem we have work total equals delta K, and we can split work total into the work done by conservative forces plus the work done by non-conservative forces plus the work done by external forces, such as pushes and pulls by people or tensions or whatever else. But we know that for conservative forces, we can replace the work done by conservative force by negative delta U. We know that for friction, we can replace this work done by the non-conservative force by negative delta E thermal. And of course, we leave the work done by external forces alone. Now we expand the delta U as U final minus U initial, and the delta K as K final minus K initial. And then we pull over the initial terms to one side and the final terms to the other side, and so we have K initial plus U initial plus work external equals K final plus U final plus delta E thermal. And so we see the truth now of our previous statement that the mechanical energy, that is K plus U, is conserved if, that is K initial plus U initial is equal to K final plus U final, if there is no external work and if there are no dissipative forces doing work. So yeah, so all these are different forms of the work energy theorem, and which one to use depends on what the situation is, what information you have, and use them appropriately depending upon if there are external forces doing work or if there are non-conservative forces doing work, which form you would want to use varies, but they are all valid. All right, so let's actually put that to the test and use them in solving a problem where there is friction. All right, so take a few moments to read this problem, and then in the next slide we're going to solve it. All right, so in this case there are no external forces doing work, but we do have non-conservative forces like friction doing work. So let us set up the energy conservation like this. We have K initial plus U initial plus the work done by friction is equal to K final plus U final. All right, well, as the initial situation, we will take the case when the mass is pressed up against the spring, so the spring is at maximum compression, and that compression is what we want to find. Let's call that S. And the block is at rest, and then it's released, and the block slides, and then it slides over the surface with friction, and it comes to a stop. And that point when it comes to a stop will be our final situation. All right, so the only kind of potential energy here is spring potential energy, because the height of the objects isn't changing, so we don't need to worry about gravitational potential energy. Okay, so let's plug in some expressions. All right, so the initial kinetic energy is 0, the final kinetic energy is 0, the final potential energy is 0 because the spring is no longer compressed. The initial potential energy is 1/2 ks squared, and the work done by friction is negative force of friction times d. Remember that the minus sign comes from the cosine 180 degrees because the force of kinetic friction is pointing in the opposite direction to the motion of the block. Okay, so we know most of these things except S and the force of friction, but this is kinetic friction, so we can use the kinetic friction formula. And so we have the force of kinetic friction is the coefficient of kinetic friction times the normal force, and in this case the normal force is going to be balanced out by the weight of the block, and so we have mu k times mg. And yeah, plugging that in, we have this equation. We know k, we know mu k, we know m, we know g, we know d, and so we can solve for the initial compression, which is S. All right, and that's how we solve that problem. All right, here is one final problem. Let's take a look, and in the next slide we'll try and solve it. So take your time, try and solve it by yourself first, and then we'll move on. Okay, so in this problem we are going to use not only energy conservation, but also what we know about projectile motion. So let's start with the projectile motion part. The ball goes off the edge of the table with some velocity and then lands a horizontal distance d away. Now, if we remember what we learned in projectile motion, we'll see that the distance d is determined by the x component of the velocity times the time that the ball spends in the air. And if we think further about it, we realize that the time spent in the air is something that talks about the y direction of the motion. And at the initial point, when it just goes off the table, the ball only has an x component of velocity. It doesn't have a y component, so vy initial is equal to 0. And so all that determines the time it spends in the air is the initial height in the y direction, as well as the acceleration due to gravity, which is the acceleration in the y direction. Okay, So we realize that when we change the compression of the spring, neither of those factors is affected. And so the time that the ball spends in the air will not be affected when we change the compression of the spring. However, Vx will be affected, and that is what is going to change the horizontal distance that the ball covers. So let's leave t alone and focus on what happens to Vx. Okay, so now we're going to the energy conservation part. Alright, so we're going to use k initial plus u initial equals k final plus u final, but what is our initial situation and what is our final situation? Our initial situation will be when the spring is fully compressed and the ball is at rest, and the final situation will be when the ball is just about to leave the edge of the table. So we're focusing on just this initial part of the motion. Well, in that case, the initial kinetic energy is zero because the ball is not moving when the spring is fully compressed, and the potential energy is the spring potential energy, and the final kinetic energy is up here. It's 1/2 mv squared. The ball is just at the edge of the table, and there is no potential energy. We're looking at just the spring potential energy here. So in other words, we have implicitly assumed that the level of the table is where the gravitational potential energy is zero. Or even if we don't assume that, basically the height of the ball is not changing during this first part of the motion, so there is no change in the gravitational potential energy. Alright, so now we can solve for V. And doing so, we see that V is equal to S times the square root of K over M. So how does this help us? Well, this tells us that if we double the compression, right, that the spring sees in the beginning, if we double that compression, then that doubles the velocity of the ball once it's left the spring. And at the moment it leaves the table, all that velocity is the x velocity. And so if we double the x velocity, then we will double the distance that it covers horizontally. And that is the solution to that problem. Alright, that's the end to this video on energy conservation, and the next video will cover potential energy curves and the forces, the conservative forces that we associate with potential energy.